Hey, how's it going, guys? Marini here with another stats video. This is going to be Tuesday's lesson on how do we perform two proportion z-test. Not to be confused with what we did on Friday, which was a two prop z interval. So Friday and today's lesson, Monday, we're both on constructing a confidence interval for the difference in two proportions, or for today's lesson, difference in two means. Now, if you remember back when we did chapter 8, that was all about confidence intervals. And then right before this craziness began with the coronavirus, we had done chapter 9, which was on hypothesis tests. Ho, ha, alpha levels, things like that. When P is low, reject the ho. So now we're going to go back and do the same thing again, but instead of doing it with one group of people or one sample, we're going to do it with two. So if you didn't get a chance to read the do now question, you can go ahead and pause the video. All right, now that you had a chance to read the question, what I'm going to do is I'm going to go ahead and actually make this confidence interval. So 0.018 minus 0.034 comes out to be negative 0.016. And when you add 0.034, you get a positive 0.052. So this is the confidence interval, specifically a 95% confidence interval for the difference, non-athlete minus athlete, in the mean reaction time. Does the interval provide convincing evidence of a difference? Is there evidence that the two proportions are different? All right. Do athletes have a faster reaction time than non-athletes? While looking at this confidence interval, I notice that it contains the number 0. 0 is in between those two numbers. So I'm going to go with no. There is no evidence of a difference because 0 is in the interval. Just to clarify, again, is 0. If there's a 0 difference in reaction time, in the mean reaction time, 0 means that there is no difference. So it's possible that there is no difference in the two reaction times. So we don't have evidence that they're different. Now, let's take a look at what I want to show you guys how to do today. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1990, 450 showed some hearing loss. In a similar study of 1,800 teenagers reported in 2010, 351 showed some hearing loss. So we have here two different groups of people. We have 3,000 randomly selected teenagers from 1990, and we have 1,800 teenagers from the year 2010. And in each group of people, we have a different amount of people, different amount of teenagers that reported some hearing loss. So here's the question. Do these data give convincing evidence that the proportion of all teens with hearing loss has increased at the alpha equals 0.01 significance level? So as soon as I see that, my brain automatically flocks to null hypothesis, alternate hypothesis, things like that. But we've never done one with two samples. So although the 4 steps are going to be very similar and a lot of this is going to come back to you, some of it's going to be a little bit different. So step 1. We just got through 2 lessons where we were writing we want to estimate, but since we're not doing a confidence interval, we're doing a hypothesis test. We want to test a claim about. And since this is a proportions question, and it's talking about the difference between two proportions of teenagers that have shown hearing loss, we want to test the claim about the true proportion difference in hearing loss between, and let's just add some context, teenagers Okay, now we also need a null hypothesis and we need an alternate hypothesis. In your null hypothesis, you're going to go on and you're just going to say that there's no difference in these proportions. The proportion of teenagers that had hearing loss in 1990 is the same as the proportion of teenagers that had hearing loss in 2010. And the way that you can show that, one way that you can say that, is that P1 equals P2. The two proportions are the same. And we'll write down what P1 and P2 is contextually in a moment. Your alternate hypothesis can be a less than symbol, greater than symbol, not equal to symbol. Kind of depends on what we're looking for evidence for. So let's go back and read the question. Does this data give convincing evidence that the proportion of teens with hearing loss has increased? Okay, increased. That means that the people that have hearing loss, or the teenagers that have hearing loss, the proportion of them would be greater than, or it would be greater in 2010 than it was in 1990, or the proportion of teenagers that had hearing loss in 1990, which we can say would be P1, would be less than the proportion of teenagers that have hearing loss in 2010. So we're going to go ahead and label P1 to be the true proportion of teenagers with hearing loss in 1990. And then P2 would be the same thing, but teenagers in 2010. Okay, so that's a little bit different. All right, we have two different proportions. Your null hypothesis is always going to be that they're equal to each other, meaning that there's no difference in the proportions of hearing loss between these two groups. And your alternate hypothesis, because I'm setting it up where P1 is the hearing loss of teenagers in 1990, that I'm saying that that's less than the hearing loss for teenagers in 2010, because we're looking to see if it increased over the years. Step 2, I'm going to check our conditions. But before we do that, we're going to state our procedure. This is a 2 proportion z-test. And for those of you with the luxury of having a graphing calculator, when you go to stat and tests, this is number 6. So it says in the problem that we already have random samples, so we're good to go with that. Now we got to check our 10% condition for independence, so we're going to go ahead and assume that there we're greater than or equal to 10 times sample size for the first group of people was 3,000. So we're going to assume that there's 10 times 3,000 teenagers in 1990. And we're also going to assume there's got to be greater than or equal to 10 times 1,800 teenagers in 2010. And we can go ahead and check those off. Normal. Well, now we're back to proportions. So we can't use the central limit theorem. We got to check our n times p hat and n times 1 minus p hat. However, we have two groups of people. So we're going to have to go ahead and basically check 4 things. One thing, Okay, so sample size 1, people from 1990 to 3,000. So p hat 1. Let's do this over here. P hat 1. This is the sample proportion of teenagers that have had hearing loss in 1990, which is 450 out of 3,000. I got that from the problem, which is a proportion of 0.15. So that will go in here. So then 1 minus 0.15 is 0.85. And when you do this math, both those things come out to be greater than 10. Sample size 2 is 1,800. P hat 2 would be, out of those 1,800 teenagers from 2010, it said that 351 reported hearing loss. So that is a sample proportion of 0.195. One minus 0.195 is 0.805. And again, we're fine there as well. So it meets all our conditions for inference. So now we can go ahead and do step 3, which is our formula part. Now, with the formula, again, we're going to get the z-score, we're going to get the p-value, and then we'll analyze that p-value in our conclusion. So, the formula for a 2-prop z-test is z equals p hat 1 minus p hat 2 over Now, you might be wondering at this point, did Mr. Marini just make a mistake in the denominator? Should that be p hat 1 times 1 minus p hat 1, p hat 2 minus 1 minus p hat 2? Well, that's not me being lazy. That's regular p hat. We have to find out what regular p hat is. And the way that you do that is by combining these two groups together. So regular p hat is going to be, add up your denominators. So there are 3,000 teenagers from 1990 and 1,800 teenagers from 2010. That is a total of 4,800 teenagers. And add together those numerators, which is 801. And that gives you a p hat of 0.167. So that's going to be what goes in the formula. All right, so p hat 1, p hat 2, and now the regular p hat, which is 0.167. And then 1 minus that, which is 0.833. All right, graphing calculator, go down to number 6, punch in everything that it asks you for. And ultimately what happens is we get a z-score of negative 4.05, which turns into a p-value of 2.58 e negative 5. Now remember, that's a very, very, very tiny p-value. That's ultimately 0.0000258. That's very, very low. And our alpha level is 0.01. So let's go ahead and interpret that. Remember, when the p-value was low, we say that it is statistically significant. So we're going to reject the null hypothesis. When p is low, reject the ho. And that means we do have evidence for the ha. That now, there's a couple ways you could write this. We can go ahead and write that we have evidence that the proportion of teenagers with hearing loss in 1990 is less than the proportion of teenagers from 2010. Or, if you go back and read the way the question was worded, does data give evidence that the proportion of teens with hearing loss has increased? Well, it has, yes. So you can word that however you'd like. We do have evidence that the proportion of teens with hearing loss has increased okay, but another way of wording that would be, we do have evidence that the proportion of teens with hearing loss in 1990 is less than the proportion of teens with hearing loss in 2010. Ultimately, that's the same thing, however you want to word that. So that is how you perform a two-prop z-test. And you guys have a practice example down here. I'll see you guys in the Google Hangout. Only a few more lessons left to go in Chapter 10. And again, when I have more information on what's actually going to be on the AP this year, we will go ahead and practice just that stuff.